In this video, we'll continue our discussion of simple linear regression. Now, one of the things that we need to talk about as part of this discussion is a problem that arises when I'm trying to fit a line to data. So hopefully you can kind of see my random data points that I'm drawing here. All right, cool. And so I'm trying to fit a line, if I can, to this data set. Let's say that one. Well, maybe that's not good. Let's say that one. Oh, I can probably do a little better than that. Let's say that one. All right, and assuming all these are straight lines, the problem that arises with this is which line is best for this data. I've got three options, all of which are pretty close. Which one's better? And actually this gets pretty problematic because like these are differences you can see, but on a computer I can get to fractions of a decimal place where I'm looking at the difference between these. So lines that are so similar you almost can't even tell that they're different. How do I objectively determine which one is best? That is, again, part of the point of statistics is to not say this stuff subjectively, not to say this stuff and say, hey, you just got to trust me, this one's better than the other ones. We're trying to do this objectively from data. So how do I objectively pick one of these versus the other? Or pick which one's best? Well, actually, this depends largely on how you define the term best. And there's two common ways to define the word best. One is called MLE, and this stands for maximum likelihood expectation. So we want to maximize the likelihood of this particular line given the data. So we've got our data, or we want to maximize the likelihood of the data for a particular line. So find the line that maximizes the likelihood that the data came from this line. So that's one. The second method that we do, and this is what we'll call LSE, stands for least squares estimation. And in this particular case, and sometimes you just see it ML and LS, or even OLS. But in least squares, I want to take the residual distance, that is the distance of the error, and you go straight up in the y direction. You don't go diagonally, you go straight up. So going straight up, I want to select the line that minimizes these squared errors. So least squared error is another way that you can think about this. I want to go straight up and say I want to find the line that has the least amount of these errors, but I don't just look at the errors. If I added up all the errors, they could be 0 for a variety of different lines. I want to find the line that minimizes the squared error. So we'll use least squares here. As we get to advanced methods, maximum likelihood is a little bit broader and actually gives the same answer as least squares. But least squares is probably the easier of the two to understand, and the equations are definitely simpler. So this is the error. This is the vertical distance between my line, which is y hat, that's my best guess. Remember, the hat means estimate or guess, and my actual point. So again, the vertical distance between those two, how do I tell how far apart they are? Well, I subtract them. And I'm just looking in the vertical direction. Now, if I added all these up for a variety of different lines, I'd get 0. So instead of just adding the numbers up, I have to square the numbers so that all of the negative signs become positive. There's actually another way to do this. Take the absolute value instead of squaring. That's an interesting alternate method that you can consider. Squaring has some nicer theoretical properties, so we square. But there are methods that do different ways of getting rid of the negative sign and adding this up. Again, it all goes to your definition of what is the best line. So we're going to say this right here. This is the best line. Any line that has the smallest amount of squared error. And is this the right answer? Well, I don't know. It depends on how you define best. A bunch of different people can define it differently. But this is a pretty common way to do it. In fact, I'd say it's the most common way to do it. Again, y is your observed value. y hat is our line. It's our best guess for that observed value, moving up vertically for that particular x value. Now for this, I don't want to stress you out. In fact, the way that we minimize something, so our error equation, if we plotted this out, it's going to look like a quadratic, and we're wanting to find the bottom of it. Oh my gosh, I don't think I can do this, but whatever. That's close. You kind of see what I'm saying. We're wanting to find the minimum amount of it. So what values for B0 and B1 give me the line with the smallest amount of error? So remember, we can do this in calculus with a derivative. We take the derivative, we plug in instead of yi and y hat I, we do the beta 0. So we take the derivative with respect to B0 to find the solution for B0 and B1 to find the solution for B1. Sounds complicated. It really is just a little bit of calculus. It's not too bad. But we'll skip over that and jump straight to the answer. So the answer for B1, if I do that little bit of calculus, is I get this back. It's the sum of x minus x bar times y minus y bar. Now I do the multiplication before I add it up. So there's another set of parentheses around here. And then that's all divided by, after I add it all up, the sum of x minus x bar quantity squared. So this is the best guess for the slope when I define best using that least squares method. And so I could plug this into a computer. Actually in R, it's kind of nice because I can just do x, if I have a vector called x with all my x data in it, minus mean of x, and that gives me my x minus x bar component. I could do this for y, and then I'd multiply the two together with parentheses around them and use a star because I can't just write them next to each other in R. And then I'd use the sum command to add them all up, and then I'd divide by sum, x minus mean x, parentheses around it squared, and I'd put the squared inside the sum instead of outside the sum, and that's going to be a common mistake. So actually in R, this works pretty quickly, and the math to get here is a little bit annoying, but just involves a little bit of calculus, and once you get here, you plug it in, and you very magically get the best guess for this B1. And again, it's not magic, it's just a little bit of calculus to figure out where the curve is lowest. What B1 gives me the lowest point on the curve? That's all I am solving for. Then, after I have B1, I get B0. What B0 gives me the lowest point on the curve? And this equation is kind of surprisingly very easy once you have B1. That is your estimated value for the slope parameter. You just plug in your average y minus your estimated value times your average x, and that gives you your B0, your estimated value for the intercept. So it's really not too bad to do the intercept once you have the slope. The slope's a little tricky, but again, it's kind of nice. You don't have to do any calculus. You just plug in your values into that equation, and it spits out the best answer, mathematically the best answer. It's pretty cool that you can pick between those infinite number of lines. And using a little math and that equation, you get the best slope possible. Pretty fun. All right, so let's try an example. Let's work through this together. So I'm looking to see if the number of TV ads impacts the number of cars sold. So I'm going to change up the number of TV ads per day and then look at the number of cars sold. The first thing is that you have to realize, and this is a subtle point, we don't really talk about this a ton. We kind of imply this, and I apologize. I'm as victim to this as anybody. But if I look at my line with my little dots around it, for this kind of line, it's so important to realize when I look at a real world situation, the relationship between like the number of TV ads, as the number of TV ads goes up, I'd expect the cars to go up. You know, this isn't exactly this data situation, but this is kind of what I'm expecting. Like if you do more ads, you're going to sell more cars, or maybe the next day you'd sell more cars. That's a time series model. We won't get into that in this class, or maybe at the very end of class. But in this particular case, I'd expect, all other things being equal, more ads, more cars are selling. What's kind of weird here, though, and what we really need to understand with statistical relationships is it's not going to be perfect. Maybe the day was rainy and I had less cars sell on that day, this dot below the line here. Maybe it was sunny and great weather and everybody just wanted to come out and buy a new Porsche. Maybe that's the top of this, the dot above this line here. Like there's a whole ton of reasons why people buy cars that are not having to do with TV ads. So it's really important to recognize that statistics is cool because it acknowledges that your dots are far apart from the line. Our goal is to predict on average is there a relationship. Because if I do it one day and then a second day and then a third day and then a fourth day and then through all these days, yeah, it looks like there does seem to be a relationship on average through all these days. Then what I'm going to say is that that underlying trend represents the trend of TV ads, because the TV ads are something that I know is changing every day. As far as the random movement up and down, well, I don't know what that is. In fact, if you do know what that is, you can add that as another variable in your model, and make your line even more accurate than it is already. So it's important to realize our goal is not to get every dot on the line and have our line be perfect. Our goal is to acknowledge that there's a lot of reasons people buy cars, but to see if TV ads seems to relate to an overall trend going up and down in the number of cars sold. And if it does seem to relate to an overall trend, then we say, yeah, TV ads affects the number of cars sold, among other things. But we can say that there's a relationship. All right, so that's the context of how we're interpreting this. That's the context of how we interpret all regression, by the way. We also don't assume effect. We assume that there's a relationship between the two. So I don't say that TV ads causes cars to be sold or affects the number of cars sold. I say there's a relationship between the TV ads and the number of cars sold. Depending on how I set up the design. If I set up the design very, very stringently, then I can say TV ads affects number of cars sold, but we won't get into that here. All right, so I've got my X data, and again, I just went on a tirade about how we can't say causal, but in this particular case, I do think TV ads are going to affect number of cars sold, or that's something I wish I could say. So TV ads is going to be my X variable here. Cars sold is going to be my outcome, or my Y variable here. And though I know I can't necessarily make causal claims without some more information, it does help me to identify which variable is my independent variable, which variable is my dependent variable. With all this information, I go on and plug it into my equation. So plugging in each x value minus its mean times each y value minus its mean, and then summing all that up, I get 20. Plugging in each x value minus its mean, squaring that, and then adding all of those up, I get 4. So my overall slope is going to be 5. For my y-intercept, I plug in the mean of my y values minus the slope guess times the mean of the x values, and I end up getting 10. And my estimated regression equation, this is the best I can get with sample data, is 10 plus 5x. Looking at a picture of this, I see I have my y value, the number of cars sold. It does seem to go up with the number of TV ads. Now we can do statistical significance testing here to see is there a statistically significant relationship, or maybe this was just by chance. But looking at this, at least in the sample, I see an increase. Now actually this is a pretty good time to talk about the meaning of each of these values. So what is the meaning of 5x? We already talked about this earlier, but as my TV ads goes up by 1, so for a single unit increase in x, y goes up by whatever this number is. So this is the coefficient of x always. This is what this means. So as x goes up by 1, y goes up by 5. Now, if this number were negative, y, instead of increasing by 5, would decrease. So this would say DEC in y. So for every unit increase in x, the number in front of x is how many units y increases. Now, in this case, what is a unit? Well, it's a TV ad. So we can get more specific than that. What I just said, for every unit increase in x, there's a 5-unit increase in y. It's very cold and statistical. What does this actually mean? Well, every TV ad I sell, at least according to this pattern, if this pattern's true, again, this is our estimate. I don't know that this is actually the underlying number, but let's say it is. I know this is true for the population. Then I would say for every TV ad you do, you're going to sell 5 more cars. Well, that's interesting to know. Every TV ad you add, every TV ad you run, on average, you're going to sell 5 more cars. For every increase in the number of TV ads, this represents the increase in the outcome. Now, is this good or bad? Well, gosh, it kind of depends on how expensive TV ads are and how much profit you're making on your cars. If TV ad costs about the profit you make on one car, well, then this is fantastic. Run several TV ads. Now, is there probably a practical limit to the end of this? Yes, but remember, in simple linear regression, we just have a line, so we assume it goes on and on and on to infinity. If you run a billion TV ads, you get 5 billion cars sold. Probably not true. But in simple linear regression, for a localized example, we'll look at it that way. And that is one thing. It's called extrapolation. We don't tend to like to go beyond the data in our model. So the data is up to 3 TV ads. So that's about how far our regression can support conclusions. In any case, we're talking about basic conclusions here. In the basic conclusion, for every extra TV ad you get, you sell 5 more cars. All right, so that's the slope. What does the intercept term mean? Well, the intercept term says, well, if I keep this line going out, and you can see just how bad my cursor is, this is where the line runs into my intercept. So when I sell 0 TV ads, or when I buy 0 TV ads, how many cars am I going to sell? And in this case, we'd say, well, if you didn't get any TV ads, you'd sell 10 cars. Now, I don't have any data out here, so this is an extrapolation. What I just mentioned we want to avoid. Only look at what we have data for. But this is only an extrapolation of 1 TV ad. I'd want to be a little bit careful. Sometimes at the 0 marks, things get a little bit funky. But, you know, that is the interpretation of what this means, or what this would mean if I had data supporting this, is that at 0 TV ads, I would have 10 cars sold. Or in general, when X is 0, what is the expected number on average of Y? Note that this is, again, not a particular day prediction. This is saying on average you'll sell 5 more cars. On average you'll have 10 cars sold. This is not a particular point prediction. I realize that these dots are not going to be right on the line. So it's going to be a little more or a little less, and we'll have statistics to help figure out how much more or how much less. But on average, this is what it's going to be. And so this is our equation. We have the best fit line. So how do we get this line? We have an interpretation here that hopefully matches to reality. The statistical interpretation, I'll say it one more time for each. You can jot it down or rewind if you want. The statistical interpretation for the slope is the beta 1. For every unit increase in X, beta 1 is the unit increase in Y we would expect. So in this case, for a single unit increase in X, we have a 5-unit increase in Y. The intercept statistical interpretation is when X is 0, what is the expected value of Y on average? And I can say, what do we expect Y to be? Again, expectation refers to average. Or I can say, on average, this is what Y will be, or what we predict Y will be. So either one of those terms are good. We just need to acknowledge that this is a predicted value and it's on average. So those are the statistical definitions. Again, we can connect that back to the problem, and should connect that back to the problem to see what does this actually mean in the context of what we're talking about. Fantastic. Actually, one more thing I'll mention, and then we'll be done for this particular video. Sometimes this 0 value doesn't make sense. So running 0 TV ads does make sense, but like, let's say we're looking at a relationship between weight and height or something like that, with weight as the X value. An intercept value on weight, whatever that is, positive, negative, 0, otherwise, would say, what is the height when your weight is 0 pounds? And that wouldn't make any sense at all, because you're never going to have somebody who weighs 0 pounds exactly. So it's a really, really, really silly value. When you have silly values, you can do something called centering X. And I'm just going to mention it here, and we won't talk too much more about it, but center X. Pretty much what you do to center a value is you subtract the mean from it. So I subtract the mean value of x from all of the x values, and then I use that new variable, x minus the mean, in place of x in my regression. Now, centering x will not change the slope. The slope is going to be exactly the same. Centering x will change the intercept. The intercept now, instead of being referring to when x is 0, will now refer to when x is the average. So x equals x bar. This is now the new 0, and this is what the intercept will be interpreted at. So we would say that the intercept in that particular case is what we would expect when x is at its average value. And this will always make sense for a problem. So if you run into issues, this is a bit more of an advanced topic. I just wanted to mention it here in case you ever have to do this and you run into a case where your intercept doesn't really make sense and you'd like it to make sense. If that's ever a problem, you can always go back to this idea of centering and center x, and this will guarantee that your intercept is interpretable. The interpretation of the intercept would be, on average, what is y when x is at its average value. And that always has some meaning, because for x to be at its average value, well, that's right in the middle of things. So what's the average value of y when x is in its middle value is always going to have some meaning. All right, in the next video, we'll start talking about some other statistical calculations we can do, and then get into some of the hypothesis testing stuff we can do to determine if these values are statistically significant or not. I should do a heads up. We talked about interpretation before statistical significance to give you an idea of what these things are we're talking about. But typically the process when you're doing a research or even a homework is going to be look at significance first, and then if it's significant, you can interpret them. If it's not significant, we don't know that these are different than 0, so you wouldn't have an interpretation.